Hi everyone, today we're going to review this paper on X-ray study of nearby M dwarfs. This paper was written in 2021 by Megara et al. And builds on their paper in 2020 based on the new data that's available in eROSITA. So let's get started. Here I've reviewed the paper in a question answer form. So let's go through some of these questions. Firstly, why study M dwarfs? M dwarfs are the most numerous stars in the galaxy. It is important to study them as possible hosts of habitable planets. Why study X-ray activity of M dwarfs? One step in understanding the evolution of exoplanets and their potential for hosting life requires good knowledge of the host star's magnetic activity, since planetary atmospheres react sensitively to both short wavelength radiation and stellar winds. The UV and X-ray emissions of late-type stars are proxies for the efficiency of the stellar dynamos. The X-ray emission of M dwarfs can be expected to undergo drastic changes at the transition where stellar interiors become fully convective. Through their link with the dynamo, secular evolution of the star's high energy radiative output and its angular momentum should occur in parallel. M dwarfs stay in the saturation regime for much longer than G-type stars. Even for a 0.5 solar mass star, saturation may last as long as 1 billion years for half the objects, resulting in the prolonged irradiation. How are the observations made? The paper uses eROSITA on the Russian spectrum Roentgen gamma mission to measure X-ray luminosities and TESS to obtain rotation periods. So they search for the samples of M dwarfs compiled from SuperBlink proper motion survey for eROSITA and TESS data, and then homogeneously characterize the stars using Gaia data. How is data categorized in the analysis? So we see that in the analysis, there are two categories. One is the eFEDS and the other one is the eRAS1. The eFEDS is the eROSITA Final Equatorial Depth Survey, and eROSITA All Sky Survey is corresponding to eRAS1. The eFEDS corresponds to a 140 square degree large area in the southern sky that was observed in 4 individual field scans. And eRAS1, as the name mentions, is an all sky survey. eFEDS fields correspond to a small number of stars, and they present a detailed X-ray study, including the light curves and spectra. eRAS1 data is focused on global properties, taking advantage of a large number of targets provided by the all-sky survey. How is the procedure for obtaining the initial sample? So they start by matching the SuperBlink, also known as the LG11 data catalog, with the second data release of Gaia mission, which is the Gaia DR2. They do this by performing a multi-cone search in a search radius using TopCat. In this step, they found 9,638 Gaia entries for 8,889 LG11 stars with 736 multiple matches. In order to remove the multiple matches, they did a clipping in the proper motion and the J-band space. So they computed the difference between the proper motions in the LG11 catalog and the Gaia DR2, and then clipped values beyond a certain limit. And they repeated the same thing for the J-band magnitude. Finally, they cross-checked the values in the LG11 catalog with the SIMBAD astronomical database. And wherever there was a conflict, they did a BIA inspection. Finally, there were 8,917 Gaia counterparts for 8,736 targets from the LG11 catalog. How does the sample look? The Gaia CMD shows two distinct populations, the main sequence and a cluster of stars above it centered at GBP minus GRP 1.7. They take 5 mag as the rough dividing line between the two populations and show the distance distributions of these two groups in the figure on the right. Here it is evident that all main sequence stars are within 300 parsecs with a strong period around 50 parsecs, while the remaining stars, which make 3.4% of the whole sample, cover a wide range of distances from 100 parsecs to 1.5 kiloparsecs. Based on their position in the CMD and their large distances, these stars are probably giants that contaminate the LG11 dwarf star catalog. This study is focused on the dwarf stars, and therefore, in the following, we concentrate on the main sequence stars. How do we reconcile the EFEDs and our initial sample? First, they define a rectangular box on the sky that comprises of all 4 EFEDs fields. They match the LG11 catalog with this rectangular sky survey. This way, they found 31 M dwarfs are covered by the EFEDs observation. Subsequently, they removed by visual inspection the X-ray images, the objects that are inside the purple rectangle, but not inside the EFEDs field boundaries. They used the X-ray coordinates to search for X-ray detections in the LG11 Gaia sample. They based the match between optical and X-ray position on Gaia coordinates and proper motions from the LG11 Gaia catalog. To find the alternate possible Gaia counterparts for each of the 15 X-ray sources, they performed a reverse match in which they searched for all Gaia sources within 15 seconds of the X-ray coordinates from the catalog. The star from LG11 Gaia is the closest Gaia object to an X-ray source for all 14 cases. And these M dwarfs define our list of bona fide EFEDs X-ray emitters. This is the distribution in terms of distances and spectral types for the EFEDs. How do we reconcile eROS1 and our initial sample? They cross-matched positions of the M dwarfs with the coordinates of the eROS1 catalog within a search radius, and use the same approach as with the EFEDs and add some more constraints on the sample. So this way they recovered 593 M dwarfs, and these are the distributions for the same. How is activity and rotation dependent on mass? They show X-ray activity diagnostics and rotation periods versus stellar mass. We see that for a given stellar mass, we observe 2 or 3 orders of magnitude spread of the X-ray activity, except for lowest and highest masses, where the spread is smaller. At the lowest mass end, clearly only the upper part of the luminosity values are detectable in the flux limited eROSITA observations, while the high mass end corresponds to the transition to the spectral type K, which is not fully sampled in the LG11 catalog. So they fit the luminosity versus mass relation with a linear function in log-log space, finding the slope 2.81 plus or minus 0.25. The rotation period versus mass shows a bimodal period distribution for lower masses and an upper envelope of period distributions that increases for decreasing masses. So we see that there's a large spread in the lower masses, and generally there's a trend that as the mass increases, they become faster rotators. How are activity and rotation dependent on each other? With the new eROSITA test sample, we can study the regime up to rotation period of 10 days, which corresponds to the saturated regime in the rotation activity relation. The relation was always thought to be better defined in the luminosity versus Rossby number space. The latter one is defined as the ratio between the rotation period and the convective turnover time, which is not a directly observable parameter. So it's better defined in this graph. How are activity and mass dependent on each other in the saturated space? So if we limited stars to only rotation period less than 8.5 days, this is what the mass versus luminosity looks like. You see that there's not much change in the slope for the luminosity versus mass relation, but there is a small conversion from marginally negative slope to a marginally positive slope in the LX elbow versus mass space. How are the coronal temperature and luminosity dependent on each other? The eROSITA sample comprises a narrow range of X-ray luminosities limited by the sensitivity of the EFEDS observation. However, contrary to the literature sample, the stars from the EFEDS display a significant spread in the values of coronal temperature. So there is a large spread. A larger database of homogeneous coronal temperature measurements for M-dwarfs is needed to explore the TX-LX relation. Here, we use a proxy for coronal temperature, which is the hardness ratio. What are the results on hardness ratio? They use 3 energy bands provided by the ERAS-1 catalog, the soft, medium, and the hard band, and define hardness ratios as follows. So these are the hardness ratios, HR1 and HR2. It is evident that a large fraction of stars have no counts in the high energy band, and most of them are clustered at 0.2 to 0.6 HR1 band. This range of HR1 includes all but 2 stars for which we have analyzed the EFED spectra. We thus can conclude that the moderately positive values of HR1 are associated to soft plasma of 0.5 keV. Concerning HR2, the curious objects are the ones that are not in the soft limit, that is HR2 greater than -1. These can be broadly distinguished into 2 groups, one being clustered near HR2 soft bound and intermediate HR1 values, and the other scattered through the parameter space. The former ones are likely represented by M-dwarfs with slightly hotter corona than the ones at HR2 equal to -1, while for the latter one, a plausible hypothesis for their harder spectra is flaring activity. So these are probably due to flaring, and this is due to, this has higher corona. What are the results of X-ray variability? We found that 7 LG11 Gaia M dwarfs are detected with eROSITA during the both EFEDS and ERAS-1. We can see that the 2 stars have exhibited more than a factor of 2 higher LX during ERAS-1 as compared to EFEDS. We know this particular star is detected as a flare, and this is most likely also a flare. In order to quantify the systematic deviation between the brightness seen in eROSITA and RAS for low luminosity sources, they grouped the log luminosity in eROSITA with a bin size of 0.5 and calculated for each bin the mean of the ratio between the luminosities observed with eROSITA and with ROSAT. This systematic trend supports the interpretation that the as an effect of sensitivity limit combined with intrinsic source variability. So that was the review. Hope you guys enjoyed it, and wish you good luck, and let me know if you have any questions.